Hello everyone. Semiconductor Electronics Part 3 Diode Rectifier and Special Diodes. In this video, I will be discussing about the rectifier using a PN junction diode and also about the special PN junction diodes. First, we shall see about junction diode as a rectifier. Now, a junction diode allows current to pass through it only when it's forward biased. And if an alternating voltage is applied across a diode, the current flows only in that part of the cycle when the diode is forward biased. This property is used to rectify alternating voltages, and the circuit used for this purpose is called a rectifier. If an alternating voltage is applied across a diode in series with a load, a pulsating voltage will appear across the load only during the half cycles of the AC input during which the diode is forward biased. And this type of rectifier circuit is called a half-wave rectifier. Now this is the rectifier circuit. In this case, it consists of a transformer and the input voltage is given at the primary, and at the secondary there is a diode, and the diode gets forward biased when the voltage at A is positive, and it gets reverse biased when the voltage at A is negative. And when it gets forward biased, it allows the flow of current and we get an output across the load resistor R. Now we can see the input voltage and output voltage. Now this graphs show the input AC as well as the output voltage. As we can see, only the half of the wave we get as output across R, while the negative part of the AC is removed. This is known as a half-wave rectifier. Now we can see about a full-wave rectifier. The difference is that in the case of a full-wave rectifier, we will get output for the positive as well as the negative half cycle of the input voltage. For that, we will be use a center tap transformer and two diodes. The diodes are connected as shown in this circuit diagram. In this case, the input voltage at A and B differ by a phase difference of 180 degree. That is, waveform of A is shown as well as waveform at B. Now, when A is positive, the voltage at B is negative, and hence the output voltage we get through RL or the load resistor is through D1. When B is positive, that is, D2 becomes forward biased and D1 becomes reverse biased. Then we get the output voltage through D2 and then the load resistor R. And the output voltages are shown in these graphs. Now we can see about the filter circuit. We have seen that the output voltage is in the form of pulses. So if we have to obtain the steady DC output, we have to use a filter circuit. And a filter circuit usually consists of a capacitor in parallel to the load resistor or an inductor in series with the load resistor. Since these additional circuits appear to filter out the AC ripple and give a pure DC voltage, they are called filters. Now this figure shows the filter circuit. That is, a capacitor is kept parallel to the load resistor RL. and the output voltage with filter is as shown in the figure. As can be seen in the circuit above, a capacitor is connected parallel to the load. When the voltage across the capacitor rises, it gets charged. It discharges only when a load is connected to it. On discharge, the voltage across it falls. Now as the AC cycle changes and the second diode kicks in, the capacitor charges again due to its peak value. This is again discharged due to the presence of the load. Now it is important to note that the rate of discharge depends on the inverse product of capacitor and resistor, and it is called time constant. To increase the discharge time and get a steady DC output, large capacitors are usually connected in parallel. The idea is to obtain an output voltage close to the peak voltage of the rectified current, so that we get an almost steady voltage. Now we can see about special types of diodes, and the first one is Zener diode. It is a special purpose semiconductor diode named after its inventor C. Zener. It is designed to operate under reverse bias in the breakdown region and used as a voltage regulator. This figure shows the symbol of a Zener diode as well as its voltage and current characteristics. It is made up by doping both P and N sides of the junction heavily. This leads to the formation of a very thin depletion region and an extremely high electric field across the junction even for a small reverse bias voltage. And as the reverse bias voltage increases, it reaches a voltage Vz at which the current increases rapidly. And this is due to the extremely high electric field at the depletion region. So in the above graph, we can see that as reverse bias voltage reaches the breakdown voltage of the Zener diode, there is a large current. Also note that for a negligible change in reverse bias voltage, a large change in current is produced. Hence, in a Zener diode, the voltage remains nearly constant even when there is a large change in current. This is the property that is used to regulate supply voltages. Now we can see the Zener diode as a voltage regulator. The circuit is as shown in this figure. It consists of RS and the load resistor which is in parallel to the Zener diode, while RS is in series. An increase in input voltage increases the current through RS and the diode. The voltage drop across RS increases. The voltage across the Zener diode does not change. This happens because in the breakdown region, Zener voltage remains constant despite the change in current. If an decrease in input voltage occurs, the current across RS decreases, and also the current across Zener diode also decreases. The voltage across Zener diode does not change. This is what happens in the case of a decrease in input voltage. Thus, the Zener diode helps in regulating the voltage, that is, keeping the voltage at a constant value. Now we can see about optoelectronic devices, and the first one is photodiode. This is a special PN junction diode operated in reverse bias and designed with a transparent window to allow light to fall on it. When photons with energy greater than the energy gap of the semiconductor fall on it, electron-hole pairs are generated. The diode is designed in a manner that these electron-hole pairs are generated in or near the depletion region. Also, the electric field at the junction ensures that the electrons and holes are separated before they recombine. Further, The direction of the electric current is to ensure that the electrons reach the N side and holes reach the P side. This gives rise to an EMF. So current flows on connecting an external load. Also, the magnitude of this photocurrent depends on the intensity of the incident light. The direct correlation between the two is easily observed on application of a reverse bias. Hence, a photodiode can detect optical signals. So, it can be used as a photodetector. Now, light emitting diode. A LED is a heavily doped PN junction which emits spontaneous radiation under forward bias. It is covered in a capsule with a transparent cover, allowing the emitted light to come out. Being forward biased, electrons move from N to P side and holes move from P to N side. Also, the concentration of the minority carriers is higher near the junction as compared to the equilibrium concentration. Hence, at the junction, on either side, excess minority carriers recombine with the majority carriers. This releases energy in the form of photons. The photons emitted have energies equal to or less than the band gap. Another thing to note here is that the intensity of the emitted light is small when the forward current is small. The intensity of the emitted light increases as the current increases and it reaches a maximum value. Post this, an increase in forward current leads to a decrease in light intensity. And for making an LED, special type of semiconductors like gallium arsenide are used. Then commercially available LEDs can emit red, yellow, orange, green and blue light. And the color depends on the band gap of the semiconductor material used to make the LED. LEDs are used extensively in remote controls, optical communication, etc. The advantages of LED or incandescent low power lamps are low operational voltage and power, fast action and no warm-up time required. The emitted light is nearly monochromatic and long life and ruggedness. Now we can see about solar cells. Is a PN junction which generates EMF when solar radiation falls on it. The working principle is similar to the photodiode except that no external bias is applied and the junction area is much larger to enable solar radiation incidence. So this is the construction of a solar cell. That is a P silicon wafer of about 300 micrometer is taken over which a thin layer which is almost equal to 0.3 micrometer of N silicon is grown on one side by diffusion process. The other side of P silicon is coated with a metal, that is the back contact. On the top of N silicon layer, metal finger electrode or metallic grid is deposited. This acts as a front contact. The metallic grid occupies only a very small fraction of the cell area, that is very much lesser than 15%, so that light can be incident on the cell from the top. When sunlight falls on a solar cell, the EMF is generated due to these three processes. That is generation of electron hole pairs due to light close to the junction, separation of electrons and holes due to the electric field of the depletion region. Then electrons are swept to N side and holes to P side, and collection. That is, the electrons reaching the N side are collected by the front contact and holes reaching P side are collected by the back contact. Thus, P side becomes positive and N side becomes negative, giving rise to photovoltage. So the above diagram shows an external load connected to a solar cell leading to a flow of photocurrent. The correlation is shown in the fourth quadrant because the solar cell does not draw current but supplies it to the load. Also, sunlight is not always required for a solar cell. A light having a frequency greater than the band gap suffixes. So this is the end of this video. In this video, I have discussed about diode rectifier and special types of diodes. If you have got any doubt, please comment in the section below. Thank you.